Hello everyone. In section 14.3 we're going to talk about coefficient of determination. In section 14.2 we looked at we learned how to fit a regression line through the data points. In section 14.3 we are interested in actually answering a couple of questions here. First, we want to know how reliable or adequate is the regression model in making predictions. Okay, and the second question, perhaps as equally important, is that, well, how are we going to measure effectiveness? How are we going to quantify this, the effectiveness of the regression model? So, now the answer to this question is given below. The logic of the answer to the question actually is, well, why don't we look at the total variation independent variable, and let's see what percentage of that total variation in the dependent variable is due to or explained by the regression model, okay, the regression line. Okay, so how are we going to go about this? Let me actually begin with an example here. Let's say this is the mean. Remember, the dependent variable is y. Okay, and suppose this is y bar. And I'm going to take a look at this single observation. I'm going to put that observation here, and then I'm going to call that y1. So I have a whole bunch of observation. I'm just singling out a single one observation. Okay, now the distance from y1 to y bar, there you go, that's what that is, right? y1 minus y bar. This is what we call a deviation from the mean, just like we did way back in the beginning of the semester. Okay, now right in here, when you look at the vertical distance from y1 to y bar, remember y bar is the overall mean of all y values. Well, we can take a look at this distance as there you go. Right in here, this is the what I have boxed in. This is the predicted value of y. We're going to call it y hat 1. Okay, and this is done, let's say, for x1. Remember, independent variable is x, dependent variable is y. So, as you can see, therefore, we can partition the distance from right in here, this distance, y1 minus y bar, from observation to the mean, the total mean of all y's, into actually two pieces. That's the partitioning of the deviation. So this part, notice how little the distance is. That's not much. This distance from y hat 1 to y bar 1 is what we're going to call the explained variation. Okay, and let me actually make up a numerical example here for you, and that's going to help put things in perspective a little better. I'm going to actually make up some numbers here, okay, folks? So let's say here my y1 is, let's say, I don't know, y1, I'm going to make it like 15. Okay, y bar 10, and y hat 1 is going to be 11. Okay, now the deviation of y1 minus y bar, that means from the observation to the mean, sorry about that, the observation to the mean is going to be what? It's going to be 15 minus 10, or 5 units, true? Now if you look at that, 5 units, 1 unit is the distance from the regression line to the y bar, and the other distance, this distance is going to measure 4 units, right, for a total of 5. Well, that distance of 4 units, the vertical distance, is from y1 minus y hat 1, and that's going to be 15 minus 11, and that's 4 units. So let me now write the overall deviation. So that means what I've done is, in effect, I've partitioned the deviation y1 minus y bar as y hat 1 minus y bar, right? That's from the regression line plus from the observation to the regression line. Now if you put the numbers through this, this was 5. That's equal to y hat 1 minus y bar. That is y hat 1 minus y bar. That is this 1 unit here. So that's going to be 1 plus y1 minus y hat 1 is the 4 units up here. You see that, how it works? 5 is equal to 1 plus 4. Okay, now let's see. And notice, by the way, that distance between y1 and y hat 1, right, this distance is rather large relative to the distance from y hat 1 to the y bar. Okay, so here's a case where the predicted value is too far away from the actual value, isn't it? The predicted is 11 where the actual is 15. So if I look at right now, if I look at, let's say, what percent of that deviation of 5 units is due to the regression line, then I can do the ratio of y hat 1 minus y bar to y1 minus y bar, and that's, let's see, that was 1 out of 5, and as a percent, that's 20%, which is a low number, right? That's the contribution, or that's how much actually of that deviation is accounted for due to the regression line, right? Okay. Now, let's take a look at another example. Okay, so let's now do our next example here. In this example, let me draw my vertical and horizontal axes. So this is my x, and let's draw the vertical line here, and this is going to be the vertical line. That's my y. Okay, and I have here, sorry, so this is going to be x and this is y. All right, now let me draw that blue line, which is the regression line here, and I'm going to show you now something that's going to help clarify the idea of explained unexplained variations. Okay, so this is going to be now, let's say I'm going to make a point clear out there. Okay, so forget that point. I'm going to call this y2 now. That's the actual observed value at let's say at x2. This is what I have observed. Now my green line, which is the overall mean, let's say this is the overall mean, that's what y bar is. Okay, now this time the predicted value on the regression line is that, so that's going to be my y hat 2. That means the predicted value of y using the regression line when x is 2. That's what that is. Now if you look at this vertical distance, that is this distance right here, notice how small that distance is, right? And let's do what we did before. Okay, what I want to do is I'm gonna look at the distance from the actual observed value of y2 to the mean, call that y sub 2 minus y bar. We can partition that again into 2 pieces. This time again, just like what I had before, I can write y2 minus y bar as the sum of 2 pieces, y hat 2 minus y bar plus y2 minus y hat 2. Okay, so this piece right here, that's y2 minus y hat 2. Okay, and the other piece is this piece right in here. See, I highlighted it in yellow, that piece. That one is y hat 2 minus y bar. That's this part right here. Okay, that's the highlighted part. Now let me put some numbers to these, okay, to motivate it. Let's say my y bar is 10, and y2, we're gonna make y2, let's make this, I don't know, 15 again, and y hat 2 14. Okay, so I'm making y hat 2 very close to y2, and you can see how close they are actually. Okay, so this time y2 minus y2 minus y bar, that's going to be 15 minus 10, which is y hat 2 minus y bar, that's 14 minus 10 plus y2 minus y hat 2 is 15 minus 14. So the deviation of the vertical deviation of 5 units is partitioned into 4 plus 1. Okay. Now let's look at the percentage, the ratio of the piece that's explained by the regression line. Okay, and that's going to be 1 out of, actually this time it's 4, right? I'm looking at this part right in here. Okay, y hat 2 minus y bar, that's let me show you, that's this piece right here, the highlighted distance. Okay, and actually let me do it better. There, that's actual, the actual distance is that amount. Okay, that's gonna be 4. So now 4/5, that's gonna be what, 80%. Look at the percentage now, how high it is relative to the percentage we had earlier, which is 20%. So if the distance from the regression line to the actual observation, let me go back here. If the distance from the predicted value to the actual value, if that's too high, the percentage actually turns out to be low. Okay, and the closer the regression line is to the actual value, the observed value, that percentage is high. Okay, so now the ideally we would like to be as close as possible, right? The predicted to be as close as possible to the observed value. So that means we would like to have high percentages. Okay, so there you go. That's ideal. We would like to have those high percentages. Okay, now let's try to actually generalize what you have seen here. Hopefully with these two couple of examples, I was able to explain the rationale behind how we're going to measure the effectiveness of regression line. So again, the measure of effectiveness is this percentage right in here. The closer the predicted to the actual value is, that's what that number tells us. Okay, so now here, this is what's actually in your book. Okay, so let me slide this up and I'll go over it. So what the book has done is actually it has generalized the idea that I have. Instead of y1, y2, they're using the general y hat. See here, we're looking at x sub I. This is for the ith observation. This is the actual data point up here and highlighted. Okay, and then what you see on the regression line, this is actually right there. This is the predicted value. That's our y hat I. That's what that is. Okay, and you can see it in here. That's y hat I. yi is the observed value. That's the actual observed value of dependent variable. Y hat I is predicted value. So if you look at this distance, again, deviation of observed y value from the mean, symbolically, that's going to be the yi, right, minus y bar. And the reason is because this is y bar right in here. See, that's where the y bar comes in. So that distance is partitioned into two distances. One is given right here, right, by regression, and the other part is actually unexplained. This is not explained. They call it unexplained variation, and this part is explained by regression. That's how they partition this. Okay, now let me clean some of these up so it's not too crowded, and there you have it. So it turns out that we can therefore now write this, because we want to do this for all observation now. So what we're going to look at is actually now symbolically. Here's what we're going to look at. Let me bring this up. This is right in here. This is what we're going to look at. Now, the deviation of individual observation from the mean. Remember, that's yi minus y bar. So we're going to square those deviations. And in chapter 3, again, we we faced this once before, because if you don't square them, some of the deviations about the mean is 0, right? We did this earlier, much earlier. Sigma yi minus y bar is 0. So to remedy this, or to correct it, what we did is we squared the deviations, and that's what this part is. Okay, that's the square of the deviations. Now, the sum of square total, therefore, is going to be total of these square deviations. That's what they call SST, sum of square total. Okay, or total sum of squares. That's what that is. And the other portion we looked at was y hat I minus y bar. This is this called sum of squared regression. That's the distance from regression line to the mean. Okay, this is from regression line to the overall mean, that is overall mean, and that's y bar. Okay, so that's what that is. We want this to be as large as possible. We like this to be large, because that in a moment you'll see we're going to get a ratio of SSR to SST, and that's exactly the percentages I had up there. Now this portion, which is called error, that's the deviation, that's the other part of that deviation, yi minus y hat I. Okay, let me go back up here, and yi minus y hat I is actually this distance right there. Okay, that vertical distance. Okay, that's what they call the error or unexplained variation. Okay, and that's the error sum of a square. Okay, now some call it error, some call it the residual, and some informally call it the miss, how much you actually missed it. That's the miss between the actual and the regression line. That's by how much the regression line missed that observation. Okay, and it's going to be what we call unexplained portion. Okay, the regression part, this one, the regression one is explained. Okay, and that's what that is. Now, from this we can actually get this, what we call the regression identity. Now, the regression identity indicates what we knew already. Remember, we partitioned the distance, vertical distance, into two parts, and that's what this equality tells us, that identity, that the total sum of a square is made up of regression sum of a squared plus the error sum of a squared. Okay, and if I write that symbolically using the notation that's directly above the red lines, SST, that means sigma of yi minus y bar, you square them, that would be equal to the regression, that's sigma y hat I minus y bar squared, plus the unexplained or the residual, which is yi minus y hat I squared. Okay, and there we have it. And finally we get to what was the title of this section. The metric for measuring the goodness of the regression equation is this measure right in here, known or called coefficient of determination. Okay, and what exactly it determines? It determines the percentage of variations in the y values that is explained by, or it is due to, the presence of independent variable, our predictor. Okay, and that's r squared, which is SSR over SST. There you go. It's a simple ratio. Now, r squared here is a percentage. Okay, so for example, if r squared is 0.8, that means it is 80%. So we interpret that as a percent. and it's indicated in the definition. See, proportion of variation means percent of variations. Alright, so that's what r squared is. Now, remember, the larger the r squared, the better. Now, let me write that. The greater the r squared, the better the model. And that is the regression model, the linear model is. Okay, now, being the ratio of the regression sum of squared to total sum of squared, the best that could happen to us, folks, is this. This is the best that could happen in any regression. These are the observed and predicted values. They're all the same, right? This falls exactly on the regression line here. Okay. Now, okay, so let me label the axes here. This would be the x and that is y. And so this is here actually the actual and observed, and the predicted values are all the same. So let's say green is predicted, and this is the regression line. Okay, green is predicted, and these other solid dots are actual. Notice that they're exactly the same. So in this particular drawing, if you look at y minus y hat, that's going to be 0, isn't it? Right? Y is the actual, y hat predicted, y minus y hat is 0, and this was the unexplained, right? The unexplained deviation. The unexplained deviation is 0, means actually when unexplained is 0 means everything, all the deviations are explained for by, right? And let me just hypothetically, let me draw this line, call that y bar. So if you look at now the distance, that distance is going to be y minus y bar is going to be exactly equal to y hat minus y bar, right? Because they're exactly the same. The y and y hat are the same. So you can see that the most, this is the regression deviation. Okay, the most that this regression deviation can be is y minus y bar, right? So that tells me that SSR is going to be always less than or equal to SST. So the best case for SSR is to be exactly equal to SST. Okay, and so when they're exactly equal to r squared, which is the ratio SSR over SST, when they're exactly equal, that's going to be 1. And that's when SSR is equal to SST. There. Now, the lowest this number can be is, by the way, is 0. When SSR is 0, and that ratio becomes 0 over a finite number, which is 0. Therefore, to make a long story short, r squared ranges between 0 and 1. 1 means perfect fit of the regression. That means all the points lie on the line. That's what that is. And 0, what 0 tells us is that this is poor fit. Okay, means the regression line has no predictive power. Okay, and there we have it. So all we gotta do is form this one ratio and we're good to go. Now we're going to actually rely on the StatCrunch to do this. Okay, but let me now to kind of wrap things up for you. Let me just write a note here. When we call explained variation regression, the variation of regression line from the mean is called explained variation. So why do they call it explained? Because this actually shows how much a deviation from the mean, okay, from the mean, and call it y bar, is reduced when the regression line is fitted to the points. So that's why it's called explained variation. Remember, therefore, the deviation of regression from the overall mean is called explained deviation, because it shows again exactly how much of a deviation from the mean, the total deviation from the mean of an observed value, that is, y bar, is reduced when the regression line is fitted to the points. Okay, so now let me actually bring up an example. We go to StatCrunch and actually do an example where we have to find these, just the R squared. Okay, so let's take a look at this exercise. We actually looked at this exercise in section 14.2. If you recall, this is the exercise on the custom home prices in, I believe it was in Phoenix, Arizona. Exercise number 52 is originally the exercise that we worked in section 14.2. So we did fit a regression line through these data points, and we got it already, but we just want to work the rest of this exercise in this section. So in part A of the exercise, the question asks us to compute the total sum of squared, the regression sum of squared, and the error sum of squared. Okay, now all three of these are going to be on the regression output. And in part B, the question asks us to compute the coefficient of determination, and that is R squared. In part C, determine the percentage of variation in observed values of the response variable explained by the regression. See that? Explained versus unexplained right in here. Explained by regression, and interpret your answer. So we'll do that in part C. And finally, in part D, state how useful the regression equation appears to be. Okay, so I went ahead and copied the regression line. I'll show you again in a moment how you actually run that regression, because we did it in the previous section, just to review it in this section as well. So once I ran the regression run for this exercise, this is actually this piece we already got before, and here is where the R squared is. RSQ means R squared. There's our R squared value, and this is the value of R squared. Okay, so it's already on there on the output. Now remember, this is a percentage, right? R squared is a percent, so this number is actually going to be about 69%, right? Roughly rounded to the whole percentage. And this is what the ANOVA looks like. Now to answer part A, SST, SSR, SSE, let me show you these in the output. So the model here is the regression model. So this is the SS, or actually not the SSR, but this is actually the regression model. Regression. Now the SS here means sum of squares. So let me put that here, actually write it. That means sum of squares. Again, those are the square of those distances, so that's why that's what the reference to the squares are. Now, so the number that sits in here is SSR. Okay, that's the SSR. Now, the way StatCrunch calls this, it calls it the model, but it's the regression model. Okay, and this other row right in here, the error, that's self-explanatory. That's the E. The regression was the R, and the SS column where E appears, so it's the row column combination. Row column combination here. Okay, that's going to be 24,882. That's the SSE that we're looking for. Okay, and the total sum of squared, that's the SST, that's this one. right in here. That's your SST, and you can see that's your T for total. And as you can see, the regression output gives you all your sum of squares. Now, one thing I have here, I got on both sides of the screen. I'm looking at actually on this side right now. Okay. And because I see a p-value, anytime you see a p-value in any output in your lifetime, okay, anytime you look at a statistical output and there's a p-value, means the output is testing a hypothesis. Now, what it tests depends on, where it appears in front of what statement. So in this case, what is this p-value? And it seems to be rather small, huh? So I don't know let's say what it's testing, but whatever it is testing, it looks like it's going to reject that null, isn't it? REG, reject, because p-value is so small. So there's actually this hypothesis that the p-value is testing is right in here. Okay, this hypothesis is actually testing the null hypothesis, or I should say the p-value is testing the null hypothesis that the linear regression model with our predictor variable x, in this case size, is not the right model for predicting the price. So this is kind of like a global test of hypothesis that the model is not an adequate model. That's another way to look at it. We have the wrong model. And since we're going to reject this null, we're going to reject the null based on our p-value, right? Because it's so small. Therefore, we're going to say, no, this is actually a good predictive model. So that's just on the sidebar what that p-value is telling us. Now, from this section, what we would like to answer is the R squared. And right in here, we have the R squared is 68.68%. So we answered all parts here, A, B, and C. Now, how useful? Well, the explanation, I'm doing that in a moment. But here's the explanation. So 68, almost 69% of the total variation in home prices, right? We're looking at prices, are explained by, or they are due to the size of the house. About 70%. Now, the other 30% is unexplained variation. So why are those home prices so different? Well, 70% of the reason the price of homes are so different is because of the sizes. Okay, the other 30% could be other amenities. It could be other attributes of the house. So, for example, how old it is, maybe the lot size, how many car garages, how many bedrooms, how many bathrooms, and things like that. All of those collectively explain for 70% of the remaining variation to bring it up to 100%. And with those other stuff, we get into the subject of multiple regression, which we will not address in this course. That's beyond the scope of our course. Excuse me. Now, as far as part D goes, right in here, part D, state how useful the regression model is. Well, this is the metric that I use in order to determine, to quantify, if you will, the adequacy of the regression model, how adequate it is, or what's the predictive power of this model. R squared equal 1, right in here, that's the best case possible. Okay, that means 100% predictive power. At this point, if that ever happens, which seldom does, the model actually becomes a deterministic model, means there is absolutely no error in it. But anytime you collect data, there's going to be error, so that is seldom achieved. Okay. Now, the rest of it actually appears in a range. So anything between 0.8 and 0.1 for R squared as a decimal, it's tagged as a strong predictive model. So the model is very strong in predicting the value of y from the knowledge of x. And it kind of gets worse as you go from 1 towards 0. With 0, this model is very poor. There is no predictive power whatsoever. No predictive power. Using x, whatever x might be, to predict y. And that's what the 0 signifies. And you can kind of see, again, you got all sorts of things in between. You get into 0.7 to 0.8, the model is adequate. And then once you get into, let's say, around 0.4 to 0.7, the moderate, nothing to write home about. And of course, anything between 0.4 and 0, right in here, the model is a poor model for prediction. Okay, this R squared, by the way, is also used in multiple regression. That's when we have multiple independent variables. So there you go. That's all we had to do in this section. So let me go on with that. Let me go to StatCrunch and just kind of remind you how the regression run was done in chapter 14. So there I have it. And let me exit out because I just ran it. So I assume you can find your way to StatCrunch, right? You go to our MyMathLab portal and then click on StatCrunch, and it opens the StatCrunch with data sets. And I actually imported the data set from the book, number 52. So here it is, the regression run. We go to Stat, scroll down to Regression. Simple linear is what we're doing. Click on that. And then we want to select our variables. Well, x, where is x? X is the size. Remember, that's our predictor. Y is the price. We want to predict the price of a house from the size of the house in compute. There's nothing else I had to do for that one. That was pretty easy. And this is the regression that I just showed you. I cut and paste the top. And I didn't do anything with this table, with the parameter estimates, but you can kind of see that 140 up here, it reappears down here. The slope of 15.89 up here reappears here. And remember, there's p-value here. Anytime there is a p-value means their hypothesis is being tested. What this hypothesis is actually testing, this p-value, 0.2933, this says the slope is, the y-intercept is 0. We don't care about that one, because if y-intercept is 0 means this regression line runs through the origin. Usually we don't restrict it. We're going to let it fall wherever it may. And then this other p-value, which is very small, we're going to reject some null hypothesis here. Here with this one, the null hypothesis is saying the slope is 0. And we're going to reject that one. Remember, slope 0 means you have a flat line. So we're going to reject that one. So I just want to tell you what these are. If you want to know more about this, you're welcome to read chapter 15. Unfortunately, we will not cover that chapter in this course. But chapter 15 talks about inferential procedures in regression analysis. And so anyway. And here's our ANOVA, the analysis of variance table. That's exactly where I got those numbers from. Now let me actually go back and to our notebook, and just to make sure we answered everything again. Part A is SST, SSR, SSE. Let me write those down. Okay, I mean I have highlighted these, but let me actually write the answer to that part A. Okay, so the SSR, the regression sum of a squared, is this number. That's 54. Sorry about that, might pop up. Okay, so that's going to be 54,562. That's the regression sum of a squared. The error sum of a squared is going to be 24,882, and the total sum of squared is 79,445, call it. Okay, and just to kind of show you where that's number 68% has come from. This number, where did it come from? How was it calculated? It's actually pretty easy. R squared is SSR divided by SST. So if you actually divide 54562.449. I'm looking at the table, the ANOVA table, where I have right here circle, divided by 79,000, 79,444.889. I bet you're gonna get 0.6868. That's how that is calculated. If you were interested, want to do it by hand, that's how you would do that. Okay, so there you have it. With that, again, we are done with this section, and we only have one more section remaining in chapter 14, and that is the section on correlation analysis. Okay, we're going to look at correlation in our next section. But for now, we are done with section 14.3.